Our next speaker is Chen Meng, and she's going to be talking about SatanGraham, which is a charm-based parallel framework for cosmological simulations.
Hello everyone, my name is Meng Chen. I'm from the Supercomputing Center of Chinese Academy of Sciences, and it's my first time to make a presentation in the USA, and I still sort of suffering from jet lag. And in this talk, I will talk about the Chen based parallel framework for cosmological simulations. And why do we need framework? Sometimes we feel like freedom when coding from scratch, but not all the Chen++ users are domain experts / CS experts. For them, it is a little hard to think in the message-driven way and feel bothered to deal with the fault tolerance and load balance. Especially if they want to migrate the old software on the Chen++, and a lot of work should be spent on design the new algorithm and architectures. And
this is not working, so
in addition to that, and now the application complexity has grown, and there are more than one developer in our team, and they need to collaborate. And to increase the productivity, we should consider the module reusing, and the code should be organized as nothing but components, and the components can be hard plugged in or out. And maybe the high-level abstract interface should be provided so that it makes the development easier. So we need a parallel framework. And the framework in this talk focused on 2 points. And one is the runtime adaptivity. And we want to make use of the XMAPP features of Chen++. And X means over compositions, and M means migratable, A means synchronous, and make use of the natural support for the fault tolerance and load balance. The other point is componentization and collaborations. Fortunately, the Cactus, an open source code, can support both of them. And there is one flash and several songs in the Cactus, and some CCL files, and the CST of Cactus can pass the CCL files to generate some glue codes, and these codes can make songs and flash stick together and compose into the final executable code. So we are talking about combining advantages of Chen++ and Cactus. Those of you who haven't used the Cactus may wonder, what does the Cactus look like? As the name Cactus, there is one flash and several songs in it. And in each song, there are source code and CCL files. And there is a special song called driver songs. It can provide parallel support. And in the flash, the main function is located in it, and the main functions can never be modified by any user, which is the key reason why the Cactus support collaborations. And all of this are built on MPI. In the last slide, we talk about combining Charm and Cactus. So does it mean it's enough to add a Charm plus driver zone to replace the original MPI one? The answer is no. Actually, we have to design the Charm based flash and a brand new parallel zone. First of all, we should do some data encapsulation work for parallel objects. And for the computing based on structured mesh, the private data for each element of array chairs is one patch of mesh. And except that, we also should do the other data privatization because in the MPI-based flash, there are global or static variables of Cactus interface. They are private to one process, but in the Charm flash, those variables can be shared by all the chairs in one group. And the data privatization is purely manual labor, but it is an important start to combine two things. Still, for the sake of performance, we can retain some global variables in the initialization of the Cactus circumstance. And also, there must be some new implementations of communication operations. They are P2P operations and reduce operations. For the data structure in the figure, the P2P operations means the ghost cell exchanging. And in this slide, the left part is the code in Charm++, and the right part is the users should do. They can write the keywords max or sync in the CCL files, and all the communication jobs can be done by the framework. We have mentioned that the framework can support collaborations. That is because the main function in the flash can never be modified by any user. And in the main function, there is a list of time beans. Some of in the initial part, some of in the evolution part, and like those things. And the users can write some schedule block in the files, like for example, like the schedule point CCL files, and the CST of Cactus can parse the files to generate a list of function point to each of time beans, and it will execute one by one, no matter it is function or communication operations. For the procedural-driven model, it works like this, but for the message-driven model, it does not. Because like in the CCL files, it will execute function B, and it will send the invoke a remote method, and it will return immediately. And if the function C needs the new data that have been exchanged, the answer will be wrong. So this situation can be solved by two methods. The one is using threaded entry. The threaded entry makes the function reentrant, and but it runs on user-level thread. The other one is using the event message model. It has two roles involved. They are message producer and message consumers. At last, we choose the later one, and we use the Stagger to control the full flow. It can generate message-driven codes from the procedural-oriented script, and also keeps the baseline Chen++ method running on the system-level thread. Also, we designed the user interface for reduced operations. We have seen the user only need to write some keywords like max in the CCL files, and the left things will all be done by the framework. First of all, the CST pass the files to get the information of numbers of max variables and their names, and then the framework will send the messages between the exit of scheduled functions and process the messages in the entry of the next function, next schedule function. The framework we talked about in this talk is called SatanGraham, and so far it is mainly for the cosmological simulations because its advances are directly driven by improvements of supercomputer, and there are two parts. There are potential difference in quotient solver for fluid simulations and n-body for particles. So far, we have we have finished the PDE solver based on the fifth order Venus scheme, and the data structure is like in the features, and for the 3D simulations, there are 6 hollows. This is a comparison between the codes from scratch and the codes on SatanGrahams. And if when coding from scratch, a user has a lot of work to do in creating the class declarations and definitions, and the mesh data mallocations and the distributions and all these things. But when coding on SatanGraham, the user should only need to write a simple statement in the script files. And this is just an example on fluid simulation based on a Venn algorithm. And for the other PDE solvers based on different algorithm, most of the components can be reused. The users only need to define the new ghost size and define the new functions for the different stencil computings. And for the other totally different applications, like the n-body simulations, the developer should define the new variables type for the certain communication patterns. This is a strong scaling test. We can see it is quite good, but there's no challenge in the scalability of the PDE solvers. And next, we will talk about the overhead analysis. And the overhead consists two parts. The first part is the cost of initialization.